rate of chemical reaction and chemical equilibrium. Chemical reactions are changes during which some new substances are formed. During such changes, the nature and identity of initial substance changes. During a chemical reaction, reactants are converted into products. The rate of reaction tells us how fast a reaction takes place. Study at a glance. Chemical reaction, chemical equation, word equation and symbol equation, balanced and unbalanced equation, rate of reactions, factors affecting rate of reaction, reversible and irreversible reaction. Chemical reactions. A chemical reaction is a process that always results in the interconversion of chemical substances. Chemical reactions are usually characterized by a chemical change which yields one or more products having properties different from the reactants. The reacting species in a chemical reaction are known as the reactants, and those formed as a result of the reaction are called products. Characteristic features of chemical change: change in color, change in the physical state, evolution of gas. Chemical change is of permanent nature, change in temperature. Chemical equation. A chemical equation is a means of writing out and describing a chemical reaction. It links together the substances which react, reactants, with the new substances that are formed, products. The chemical equations are of two types: word equation, symbol equation. Word equation. A word equation links together the names of the reactants with those of the products. Example: the word equation of magnesium ribbon burns in oxygen to form magnesium oxide may be written as magnesium plus oxygen reactants gives magnesium oxide products. Symbol equation. A symbol equation may be defined as a brief representation of a chemical reaction in terms of symbols and formulae of the substances involved. Example: burning of magnesium in oxygen to form magnesium oxide can be symbolized as 2Mg plus O2 gives 2MgO. Unbalanced and balanced equation. According to law of conservation of mass, it can neither be created nor destroyed in a chemical reaction. That is, total mass of the elements present in the products of a chemical reaction has to be equal to the total mass of the elements present in the reactants. That is, the number of atoms of each element remains the same before and after a chemical reaction. An unbalanced chemical equation is an equation where the numbers of atoms of different elements on both sides of the equation are not equal. Example: Mg plus O2 gives MgO, unbalanced. A balanced chemical equation is an equation where the numbers of atoms of different elements on both sides of the equation are always equal. The balanced equation for burning of magnesium ribbon in oxygen may be written as, example, 2Mg plus O2 gives 2MgO, balanced equation. Balancing of chemical equation. Balancing of a chemical equation is defined as process of making the number of different elements on both sides of the equation equal. The steps involved in balancing a chemical reaction is as follows. Write the chemical equation in the form of word equation, keeping the reactants on the left side and the products on the right side. Separate them by an arrowhead, pointing the reactants towards the products. Example, iron plus water. Arrow, ferric oxide plus hydrogen. Convert the word equation into symbol equation by writing symbols and formulae of all the reactants and products. Fe plus H2O gives Fe2O3 plus H2. Make the atoms of different elements on both sides of the equation equal. Count the number of atoms of all the elements in the reactants and products on both sides of the equation. Element Fe. Number of atom of reactants 1. Number of atoms of products 2. Element H. Number of atoms of reactants 2. Number of atoms of products 2. Element O. Number of atoms of reactants 1. Number of atoms of products 3. Number of hydrogen atoms are equal on both sides, but the number of Fe, iron, and O, oxygen atoms are not equal. Number of O atoms in the reactant H2O is 1, while in the product Fe2O3 is 3. To equate O atoms, put coefficient 3 before H2O on reactant side. Fe plus 3H2O gives Fe2O3 plus H2. To equate hydrogen atoms, now 6 on reactant side and 2 on product side, put coefficient 3 before H2 on product side. Fe plus 3H2O gives Fe2O3 plus 3H2. To balance the Fe atoms, put coefficient 2 before Fe on the reactant side. 2Fe plus 3H2O gives Fe2O3 plus 3H2. Now, the number of atoms of all the elements are equal on both sides, and therefore, the equation is balanced. Rate of reactions. The rate of reaction can be defined as the change in concentration of any one of the reactants or products per unit time. Rate is expressed in unit of mole liter raised to -1, second raised to -1. Energy changes in a chemical reaction. Exothermic reactions. A chemical reaction which is accompanied by evolution of heat energy is known as exothermic reaction. Example, carbon C plus O2 oxygen combines giving carbon dioxide CO2 plus heat. Endothermic reactions. A chemical reaction which is accompanied by absorption of heat energy is endothermic reaction. For example, mercury oxide 2HgO with the absorption of energy decomposes as mercury Hg plus oxygen O2. Fast and slow reactions. Fast reactions are having very high rate of reaction, that is 10 to 12 seconds or less than that. Example, reaction between sodium chloride solution and silver nitrate solution. reaction between potassium and water. But in slow reactions, the rate of reaction is very slow. Example, rusting of iron. Factors affecting rate of reaction. The speed of a chemical reaction can be altered by changing some factors. The factors affecting the rate of a chemical reaction are as follows. Nature of reactants. Potassium reacts more vigorously than sodium when put in water. This is because the electropositivity of potassium is higher than that of sodium. Take a trough containing water. Put a piece of sodium, light yellow colored solid, in a trough of water. It reacts vigorously, wandering in the water and disappears after some time. For example, 1 minute. 2Na sodium plus 2H2O water gives 2NaOH sodium hydroxide plus H2 hydrogen. Take a trough containing water. Put a piece of potassium, light pink colored solid, in a trough of water. Potassium reacts more vigorously than sodium and disappears after some time. For example, half a minute. 2K potassium plus 2H2O water gives 2KOH potassium hydroxide plus H2 hydrogen. Effect of concentration of reactants. Concentrated hydrochloric acid reacts more vigorously with marble chips to produce carbon dioxide gas than with dilute hydrochloric acid. This can be explained by the collision theory. CaCO3 calcium carbonate plus 2HCl hydrochloric acid gives CaCl2 calcium chloride plus H2O water plus CO2 carbon dioxide. Concentrated hydrochloric acid is poured through thistle funnel into marble chips taken in the conical flask. Colorless gas of carbon dioxide evolved vigorously and collects in the gas jar. Dilute hydrochloric acid is poured through thistle funnel into marble chips taken in the conical flask. A little amount of carbon dioxide is formed and collects in the gas jar. In case 1, number of reactant molecules is high, higher concentration. Hence, number of collisions are also unlimited. But in case 2, number of reactant molecules are less, lesser concentration. Hence, number of collisions is also limited. This can be explained by collision theory. An increase in the concentration of reactants leads to an increase in the frequency of collisions, which increases the rate of reaction. Effect of pressure. When the pressure of the reacting system consisting of gases is increased, the volume will decrease, resulting in an increase in the concentration of the reactants. When the concentration of reactants increases, the rate of reaction will also increase. Increase in pressure increases the speed of the reaction. If the total volume of reactants and products are same, then the pressure has no effect. Increase in pressure increases the speed of the reaction only if the volume of products is less than the total volume of the reactants. take 1 volume of nitrogen molecules, N2, and 3 volumes of hydrogen molecules, H2, in a closed vessel. When high pressure is applied, piston moves downwards and molecules of nitrogen and hydrogen come very close. That is, concentration increases and collision also becomes effective, leading to the formation of ammonia, NH3, very easily. Effect of temperature. At low temperature, the molecules which possess sufficient energy to bring about chemical reactions by collision are very few in number. When the temperature is raised, the velocity of molecules will increase, and there will be many more molecules which possess energy greater than the threshold energy, resulting in the formation of activated complexes. So, at higher temperature, the reaction rate is faster than at a lower temperature. Effect of catalyst. A substance that alters the rate of a reaction without itself undergoing permanent change is called catalyst. In a chemical reaction, before reaching the equilibrium, activated complexes are formed. The molecules should have a certain minimum amount of energy to form the activated complex. Often this energy is so high that very few molecules can reach that level. When a catalyst is present, it offers another easier path for the formation of the activated complex. The catalyzed route requires only a lower threshold energy. In the manufacture of ammonia, iron is used as catalyst, and it enhances the rate of the reaction. N2 plus 3H2 in the presence of iron as catalyst gives 2NH3.